Hi, I'm Dr. Neenu Garg. In this session, I will discuss process concept basics. Let's start. What is a process? On the screen, you can see multiple definitions of process. A process is a program in execution. A process is a unit of work in modern time sharing systems. A process is a running or dynamic instance of a program. A process is a name given to the activities performed by CPU. So what we understand from all these definitions is a process is a program which is currently being executed by a CPU, and a process is execution of all the instructions which are written in a program. Now let us understand this with the help of an example. Suppose you write any C program or C++ program. After writing, you compile your program using some compiler. Now this compiler will generate binary code. Notice that the original code and the binary code both are programs. The executable is a program. The executable will become a process when you actually run the binary code. Now, what is the difference between program and process? Program is a passive entity stored on disk. It includes the executable file, and process is an active entity. Why active entity? Because CPU is currently executing the process instruction by instruction. So it is an active entity. Now execution of a program starts via GUI mouse clicks, command line entry of its name. You must have seen there are several softwares in your computer system. If you want to run any application, then you take your mouse pointer to that particular icon and you just click your mouse twice. Other ways, you can open command line prompt and then you can write the name of the executable, press enter, and the application starts. One program can generate several processes. Multiple users can be executing the same program. For example, there are n users which are connected to a central server. They are running some program which is actually stored on server. Or we can say an instance of that program is running on the system of every user. Let's have a better understanding of program and process. All of us know that MS Word and Google Chrome are two softwares which are present in a computer. Your system have the executable files of these programs in hard disk. The executable of Google Chrome is chrome.exe and executable of MS Word is winword.exe. Notice the word jobs here. All the programs that are residing on hard disk are termed as jobs. When you double click on any program, suppose I want to open Google Chrome, what I will do, I will double click on the icon of Chrome. So an executable will be created, chrome.exe in the disk. It will be created in the disk C, chrome.exe written in blue. So this copy will be loaded by scheduler in main memory. The executable that was created in hard disk will be brought into main memory for execution. Before execution, it will be present in main memory. Whenever you click on the icon of Google Chrome, a copy of executable is created in disk and then it is brought in main memory for allocation to CPU. So we can now say that multiple instances of a program can be created, and these multiple instances of a program are different processes. 5 states are involved in the life cycle of a process: new, ready, running, blocked or waiting, and terminated. Let us understand each of these states with the help of a diagram. When a new process is created in disk, then the process is in new state. All those processes that are loaded on RAM and waiting for CPU are considered in ready state. After new state, a process moves from new to ready state. When the process is in ready state, it means it is ready for further execution. In this state, a process waits for the processor. Please note that in multi-programming environment, many processes can stay in ready state. Now, when schedulers select any process from the available processes in ready state, that process is dispatched to CPU for execution. Now the process is running on CPU, and so the state of process is running state. Now when the process is executing on CPU, it might need some input output. Then, and if the device is not free, it has to go in waiting state. It will wait for that particular input output device. And once the device is free and it has been served, then it will again go back to ready state. A process which is in waiting state can never go directly from waiting to running state. If it has completed its input output, it can be again allocated to CPU if and only if it is present in ready state. Now, if a process is in running state, some high priority process or some other system call may disturb the execution of process. So the process is interrupted. It goes back to ready state because the process was running and there were no outstanding requests of the process, but still some interrupt occurs. So it has to go to ready state. It will not go in waiting state. It will go to ready state. From running state, a process can go to terminated state. When the execution of process is complete, it goes to terminated state. And when a process goes to terminate state, all the resources that are allocated to a process are taken back from it. Let's now see the process layout in memory. A process contains instructions to be executed which are written in a program. Apart from that, there are more information attached with the process. Now, the program code which is associated with the process is termed as text section. If you see, a text segment, also known as code segment or simply as text, is one of the sections of a program in an object file or in memory which contains executable instructions, contents of processor registers, program counters, and so on. Next comes the stack section. Stack section contains all the temporary data, function parameters, return addresses, and local variables. Your program will be full of functions. So there can be a function call like F1 is calling another function F2 and F2 is calling some another function F3. When F1 calls F2, the return address of F1 will be put on the stack. When F2 calls F3, the return address of F2 will be put on the stack. And when F3 calls F4, the return address of F3 will be put on stack, and so on. The order of execution will be F3, then F2, and then F1. So all these return addresses needs to be stored somewhere, and that memory area is stack memory area. Every process will have its own stack area. Next section is the data section. Data section stores all the static and dynamic variables. All local variables of a function are allocated space in stack, but if any variable is declared global, then it is given space in data section. Also, a program can have dynamic memory allocation. Dynamic memory allocation means the memory is allocated at runtime. If I talk about C programming, then your program may use functions like malloc, calloc. So these functions are used to allocate this dynamic memory. This dynamic memory is heap. As you can observe, there are two arrows, upward arrow and downward arrow. These arrows indicate that the area for stack and memory area for heap for a particular process is not fixed. In some programs, there can be more function calls. In that case, there will be need of more stack memory. However, in some programs, there is more dynamic allocation, so heap will grow. So these arrows indicate that these memory areas shrink or grows depending upon the process. Let's now understand process control block. As a person, we have so many attributes like I have brown eyes, I have black hair. Every process has some attributes. These attributes are stored in process control block. In some books, it is also referred as task control block. The different attributes that are related to a process and are stored in its PCB are process ID, process state, program counter, CPU registers, scheduling information, memory management information, accounting information, and IO status information. Process ID is a unique identifier which is assigned by operating system whenever a new process is generated. Every process will have a unique ID. No two processes, even if they belong to same program, they will have their own identity. Process state. We are aware about the different states of a process: new, ready, running, terminated, waiting. So this attribute will store what is the current state of a process. Program counter. It is the location of instruction which is next to execute. For example, the state of the process whose execute. Program counter means program counter. It stores the location of next instruction which is to be executed. Now, the state of a process whose execution is relinquished by CPU has to be saved. Program counter will store the address of next instruction from where the CPU will execute it when it is reassigned to CPU by the scheduler. Next is the CPU registers. CPU registers include accumulator, base registers, limit registers, general purpose. CPU register contains general processor centric register like accumulator register, general purpose register, and so on. CPU scheduling information. So it will store about the priority of process, any pointer informations, memory management information. Memory management information stores What are the values of base and limit registers? Memory management information is required for the security of a process. One program should not interfere with the execution of another program. Memory area which is allocated to one program must not interfere with the memory area allocated to some other process as well as operating system. Accounting information. Accounting information includes CPU used, the clock time elapsed since start, time limits. IO status information. IO status information corresponds to, say, the list of any open file which is used by a process, any other device information, and so on. Now we will understand how CPU switch from one process to another. There are two processes which are shown here. Process P0, process P1. P0 is executing with CPU. At this point, some interrupt or system call occurs. So CPU has to relinquish its execution. It will save the state. It will save its state into PCB0. Saving state will take some time. Once the state has been saved, it will load the state of the process which interrupted P0. So it will load the state of PCB1. And this time P1 is executing and some interrupt occur. This interrupt can be time slice expires as well. So now interrupt has occurred. So CPU will now first save the state in PCB1. Saving will take some time and then it will reload the state of P0 back. It will take some time and then again P0 will execute. So there is an important observation here is whenever CPU leaves the execution of one process and start executing other, two important roles are done. First is saving the state of the process which CPU was previously executing and loading the state of the process which has to now execute by CPU. Saving state and loading state means saving their PCBs and loading their PCBs. And saving the state of saving state into PCBs and loading state from PCBs takes some time. These dots indicates those times. So this is a time for activity. There is a small activity for you. So there is a small activity for you. What you have to do is you have to see the active processes on your system. If you are using Linux operating system, then open terminal and type the ps command to display all the running processes. If you're using on Windows operating system, open Start, do a search for Task Manager and click the result. On Mac operating system, open Activity Monitor application. This was all about process concept basics. Hope you liked the session. Thank you.